Have you ever just looked up at the night sky and wondered if those seemingly random patterns of stars are actually telling a single, massive, dramatic story? Well, welcome to this explainer. Today, we're going to unravel a literal cosmic detective story that's been hiding right above our heads. We're digging into a fascinating recent astrophysical study that actually pieces together the lifespans of star clusters. And to do it, we're going to have to fast forward millions of years into the future. Let's get into it.
Okay, so here is the central mystery we're unpacking today. How in the world could a chaotic, super dense stellar nursery packed with literally thousands of infant stars and a sparse, dying cluster barely clinging to a few hundred members, how could they actually be snapshots of the exact same object, just at different points in time? I mean, this is a bold question. It completely upends the traditional ways we've thought about stellar evolution, and honestly, answering it requires us to completely rethink the life cycle of the night sky's most iconic features.
All right, let's dive into this. What we're looking at here are the constellations of Orion and Taurus, and specifically three incredibly famous features that you can actually walk outside and see with your own naked eye. Down in the bottom left, nestled right in Orion's sword, we've got the Orion Nebula cluster, or the ONC. Then, if we move up into Taurus, we hit that tight, super bright grouping called the Pleiades, and just slightly below and to the left of that, the V-shaped Hyades. Now, historically, astronomers have studied these as completely separate, entirely distinct families of stars, but the source material we're exploring today, it proposes a radically different idea.
When we compared these three, you instantly see why connecting them is such a massive leap. I mean, just look at their current observed states. The ONC is essentially a cosmic newborn. It's just 2.5 million years old, absolutely packed with around 4,000 stars in a really compact space. Then you have the Pleiades, which is effectively a teenager. It's roughly 110 million years old, way more physically expanded, and holding on to about 1,000 stars. And finally, the Hyades. This is the elder of the group at nearly 800 million years old, spread way out, sparse, with just 400 stars remaining. So their ages, their sizes, their populations, they're staggeringly different. Which begs the question, how on earth do you prove they're the exact same type of cluster just aging in place?
The supercomputer time machine, fast-forwarding 800 million years. So, to test this wild theory without, waiting around a billion years, researchers used something called the N-body 6 code. And let me tell you, this isn't just your standard piece of software. It's a highly advanced mathematical simulation running on some seriously powerful graphics processing units. It's not just tracking dots on a screen, it's simulating the exact gravitational dance of thousands of individual stars over millions of years. It accounts for the whole shebang: stellar evolution, supernova explosions, and even the larger gravitational tidal pull of the entire Milky Way galaxy literally trying to rip the cluster apart. But here's the catch. The scientists had to find the exact starting ingredients to plug into this time machine to see if it would actually evolve into our three famous clusters. After testing a bunch of variations, they finally landed on their winning initial setup, what they labeled Model M1.5K-S1. Basically, they perfectly replicated the birth conditions of the Orion Nebula cluster. We're talking about 4,200 initial stars, a really tight core where the heaviest stars actually sink right to the center. That's a process called primordial mass segregation, and a high fraction of binary pairs. Throw in a total starting mass of up to 2,000 suns, and they were finally ready to hit play on the simulation.
The Great Gas Expulsion, the violent turning point in a star cluster's life.
Okay, so early on in a star cluster's life, there was this massive destructive force that dictates absolutely everything. It's called gas expulsion. Basically, it's the rapid removal of residual gas from a star cluster, and it's driven by intense UV radiation, stellar winds, and supernova explosions from those massive young stars. So the crucial point is this: when a cluster forms, only about a third of the gas actually turns into stars. The rest of it, just leftover gas. But that gas acts like gravitational glue, holding all those young stars tightly together. However, those massive, incredibly hot newly formed stars act like giant cosmic leaf blowers, violently clearing out that gas in just the first few million years. Let's just walk through exactly how this completely transforms the cluster. Step 1, the cluster starts out in this tight, compact nursery, super heavy with gas that's holding everything together. Step 2, the massive stars ignite, and boom, their intense radiation just blasts the remaining gas away into deep space. Which brings us to Step 3. Suddenly, a huge chunk of the cluster's mass is just gone. The gravitational well becomes really shallow. Without that glue, the stars are moving way too fast to be held tightly together anymore, and the entire cluster physically balloons outward. It loses its outer stars to the galaxy, transitioning from a tight nursery to a loose, spreading grouping. It's a total game changer.
A cosmic time-lapse, following the clues left in the data.
All right, now we're getting to the good stuff. Let's look at the actual output from the simulation. What's really interesting here is tracking the number of stars in the cluster over time. See that really sharp drop early on? That is the violent gas expulsion phase we were just talking about in action. But notice where the actual observed star counts of the Pleiades and the Hyades sit today. The simulated cluster, which, remember, started exactly like the ONC, perfectly hits the observed star counts of the Pleiades right at 110 million years and the Hyades at 800 million years. It's honestly kind of mind-blowing how well it lines up.
And this brilliantly illustrates what happens to the physical size of the cluster. We're tracking what's called the half-mass radius, which is basically just a fancy way of saying how spread out the bulk of the stars are. Notice how it starts off low and compact, just like the ONC, but then it arcs rapidly upwards as that gas is expelled and the galaxy's gravity starts tugging at the stars. The simulated size absolutely balloons outward, completely matching the spread-out, expanded nature of both the Pleiades and the Hyades at the respective ages.
Now, the simulation reveals a pretty stark reality about the life of a star cluster. By the time our simulated cluster reaches the age of the Hyades, so roughly 700 to 800 million years, it only retains 9% of its original stars. Let that sink in for a second. A massive 91% of the stellar population has been completely lost to the cold void of space, scattered by that early gas expulsion, violent supernovas, and the relentless tidal pull of the Milky Way. So when we look up at the Hyades today, we are literally looking at the resilient 9% of a once massive stellar family. So, what does this all mean? What's the big takeaway from all this data? The huge reveal here is that these aren't three separate, unrelated stories at all. They represent a single timeline. At 0 million years, you have that compact birth phase, which is perfectly represented by the Orion Nebular cluster. Fast forward to around 100 million years, the gas is totally gone, the cluster has expanded, and it looks exactly like the Pleiades. Fast forward again to 800 million years, and you're left with the sparse, dying remnants of the Hyades. It's literally a single life cycle, just playing out before our very eyes.
As the researchers so powerfully concluded in the source paper, an ONC-like cluster may have been a precursor of the Pleiades and will be similar to the Hyades around 700 million years in the future. I mean, think about what that actually means for us. The night sky isn't just some static painting, it's a giant slow-motion time-lapse. So the next time you walk outside on a clear night and spot Orion's sword, or you catch that tight grouping of the Pleiades, I challenge you to look at them not as separate objects, but as a ghost of the past and a vision of the future. The stars are quite literally showing us their life story. Makes you wonder, doesn't it? What other cosmic mysteries are hiding in plain sight, right above our heads?